Well, we've made it to the last chapter, exponential functions and their graphs. Let a be a fixed positive real number not equal to 1. The exponential function with base a is the function f of x equals a to the x. In the past, we've always had our variable in the base part, something like x to the fourth or x to the third or something like that. Well, now our x is going to be in our exponent. So our base will be some number. Actually, it will be some positive real number not equal to 1. So let's have a look at these graphs and what they act like and what they do. F of x equals 1/2 to the x. If you have a 1/2 here, and you raise that to a -2, 1/2 to a -2 means you flip this over. Once you flip it over, the exponent becomes positive. That's where this 4 comes from. So 1/2 to the -1 would be 2. 1/2 to the 1 is 1/2, and 1/2 squared is 1/4. If you were to graph all of these, you would get this picture here. So what does it look like if our base is a whole number as opposed to a fraction? Well, first of all, it will reflect over the y-axis. Do you see how they're reflected? And since this base is higher than this one, meaning this would have been like a 2 to the -x, that's what that means, then this 3 would make this get a little bit flatter in here. It's still passing through the point 0, 1, but it's going to get steeper faster. These are some values. If you plug in -2, -1, and 2 into this function, you end up with 3 to the -2 is 1/9, 3 to the -1 is 1/3, 3 to the first is 3, and 3 squared is 9. So you can see how these numbers could get big really fast. Given a positive real number a not equal to 1, the function f of x equals a to the x is decreasing if a is a is between 0 and 1. Let me just talk about what that means. Back here on the previous screen, a is between 0 and 1 means pretty much a is a fraction between 0 and 1. Do you see how this is decreasing? It's falling from left to right. That's because our a is between 0 and 1. So what about when a is greater than 1? It will be increasing. So go back to this page. Do you see how this base is 3? 3 is greater than 1, so this function is an increasing function. In either case, the point 0, 1 lies on the graph of f. The domain of f is the set of real numbers, and the range of f is the positive real numbers. Now that happens whenever we're not adding to or subtracting from the function. Then your y will be the set of all positive real numbers. So let's have a look at this one, 3 to the -x. Like on that previous screen, that's the same thing as f of x equals 1/3 to the x. That's why this function is falling from left to right. I included a table here so that you can see what the values do as you plug numbers into the function. I've also included on the screen for you something to compare it to. F of x equals base 2 to the x looks like this one. So that's a good function to remember because you can pretty much compare all functions to this one. Have a look at these three. We're looking at B, C, and D here. There's a lot of information on this page, so let's see what we have. This is just our reminder over here. You can pause and have a look at it if you like. Now, if we were to plug some values into this first function, I've included that table here. We would get this graph. So how does this graph relate to this function? Well, this negative in front of the base will make it reflect over the x-axis. Adding 1 to this function will shift the graph up 1 unit. You remember how it used to look like this? So if we reflected, it would go this way. But if we shifted it up 1 unit, now it's passing through the origin. Okay, look at the next one. 2 to the x minus 2 and then minus 1. The minus 2 part is what's going to shift this 2 places to the right. But the minus 1 is going to shift it down 1 unit. Remember, it used to pass through this point right here. So that point would actually shift right 2 and down 1. So we take this graph and perform those transformations on it. So let's look at D. We have 1/3 to the 1 minus x. Well, the 1/3 is supposed to reflect it over the y-axis. So you would take this graph and reflect it this direction. But since we have this 1 minus x, it's doing different things to it. 1 minus x is the same thing as negative x plus 1, right? Well, that's the same thing as negative times x minus 1. So this negative reflects it back over the y-axis, and since we're subtracting 1 on the inside of the function, it's shifting it to the right 1 unit. Now, how can we use this information to solve exponential equations? What I'm going to do is let you read through these steps, but I'm just going to work the problems. So for A, what we want to do is get the thing raised to the variable by itself. So we're going to add 81 to both sides. Now what we want to do is make sure that our bases are the same. Well, 27 and 81 are not the same base. I know that I can raise 3 to the 3rd power to get 27, and I can raise 3 to the 4th power to get 81. So this becomes 3 to the 3x equals 3 to the 4th. Well, since you have like bases, and these are equal to each other, then their exponents must be equal. So 3x must be equal to 4. When you divide both sides by 3, you get x is equal to 4/3. If you were to substitute this back into the equation, you would find out that it does make this equation true. So how about the next one? We have 32 to the y minus 1 equals 1/2. I think I can use a base 2 for this one. 32 is the same thing as 2 to the 5th. So we have 2 to the 5th, and then that's still times that y minus 1 equals 1/2 is the same thing as 2 to the negative 1. So now what I have is 5 times y minus 1 equals negative 1. Distribute, add 5, and divide by 5. Y is equal to 4/5. How about C? 2/5 to the x equals 125/8. It looks like I can raise 5 to something to get 125, but that means I'm going to need to flip this over. So let me go ahead and rewrite it that way first. 5/2 to the negative x is equal to 125/8. Can I raise 5 and 2 to some power to get 125/8? I believe so. 5/2 to the negative x is equal to 5/2 cubed. So that means negative x equals 3, which means x equals negative 3.